Hello students, welcome to this lecture. This is basically the first lecture on the ionic equilibrium. In the previous lectures we have discussed about the chemical equilibrium, and ionic equilibrium is basically the part of the chemical equilibrium, and there are various equilibria that involves the ion, and that is called the ionic equilibrium. And in this from this lecture onwards, we will have a discussion on the ionic equilibrium. Basically, that is the ionization of acids, ionization of base, and pH related things that we will discuss. Hydrolysis, we will discuss all the things in this ionic equilibrium chapter. We will discuss now. Today's video that we want to discuss some fundamentals of the ionic equilibrium, which is necessary for understanding the total concept of the ionic equilibrium. So today's lecture, we can say, that is the introduction of the ionic equilibrium. Introduction of ionic equilibrium, and in this equilibrium we will discuss some fundamentals. This is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. Michael Faraday classified the substance on the basis of their capability of the carrying the electrons, or you can say electricity. Those are basically has been classified as by the Michael Faraday. That is one, that is the electrolytes. Electrolytes are the substances which in aqueous solution or in melt can conduct the electricity. So we can write in brief, in melts or in aqueous solution. Aqueous solution can conduct electricity. Can conduct electricity. Example of this: inorganic acid, base or salts. And another variety that is of the substance, that is non-electrolytes. Non-electrolytes are those it cannot conduct electricity, cannot conduct electricity. In its aqueous solution. The example that you can see: glucose, urea. So electrolytes are those which conduct electricity in the melt condition or in aqueous solution. Non-electrolytes are those substances that which are not going to conduct any type of electricity, and they are basically glucose and urea, and lot of example you will find, that is sugar solutions and all the things. They are not going to conduct any electricity in their aqueous solution. Again, these electrolytes is further classified into the strong electrolytes and the weak electrolytes. The strong electrolytes are those electrolytes which are completely dissociated in their constituent into the ions. As for example, the HCl. HCl acid is a electrolyte. We can classify as it is a strong electrolyte that it can easily fragmented, it can easily ionize, separated out with itself from each other. And in the aqueous solution of the HCl, what we found? We will found the H plus ion and Cl minus ion. And another variety, that is weak electrolytes, they are not being dissociated or ionizes into completely into their constituents. Some of the molecules became unionized, and they put a equilibrium. They establish the equilibrium between the unionized and the ionized molecule. As for example, the weak electrolytes, you can say this is weak electrolytes. Electrolyte, that is acetic acid. Acetic acid in aqueous solution, what we found, that it will make a equilibrium between the unionized and ionized. This is a equilibrium they maintained between the unionized. This is unionized and it is ionized, and this is called the ionic equilibrium. This type of ions, when their equilibrium with their unionized counterpart in the aqueous solution, we will call it is the ionic equilibrium. So we can understand what is ionic equilibrium. Now there is a terminology that we need to understand. They will be used as a similarity with each other, that is the dissociation and ionization and dissociation. They are basically different. Different in the sense, when the ionic compound has been dissolved in the water, it will be called a dissociation, and when the covalent compound dissolve in the water, it is called the ionization. So these two terminology will be used as a similar way, so the similar meaning. So now we understand what is electrolytes, non-electrolytes, weak electrolytes, and the equilibrium normally being achieved, established for the weak electrolytes. Now we are going to discuss the degree of dissociation. What do we mean by degree of dissociation? Degree of dissociation means the fraction of the moles of the electrolytes that are going to be dissociated in their aqueous solution. So we can write the degree of dissociation, that is has been denoted by alpha, and we can write in a form, that is number of moles of electrolytes, moles of electrolyte dissociate divided by total numbers of moles available. That is the degree of dissociation. Total number of moles of electrolyte has been dissociated in their aqueous solution, and total number of moles are available in it. This will be called as the degree of dissociation. Okay. Now, so we are going to discuss the factors influence the degree of dissociation. The degree of dissociation. What are those factors that we will discuss now? First factor, that is solute. So easily understand that when it is a strong electrolytes, it will dissolve much. Strong electrolyte, its degree of dissociation will be alpha is equal to 1, and weak electrolyte that will be less than, alpha will be less than 1. So if the strong electrolyte we used as a solute, then it will have the higher degree of dissociation, and for the weak electrolytes it will be less. Then the solvent. If the solvent used is a polar solvent have higher degree of dissociation. Because the polar solvent like H2O, it is having the high dielectric constant. The ionic products, you know, they are being connected with each other. There is a electrostatic force of attraction between the positively charged and negatively charged ion. So this electrostatic interaction is inversely proportional to the dielectric constant of the medium. So when it is dissolved in water, as because it is having the higher dielectric constant, it is about 80, then what is going to happen? This electrostatic force of interaction will be weakened by a factor of 80, and that is why when we put some NaCl, which is a electrostatic compound, in air water, it will separate out very easily. But for acetic acid, it is not like so. For acetic acid, if we put the acetic acid in H2O, it will behave as a weak electrolytes. But if we put acetic acid in NH3 solution, then it will act as a strong electrolyte. At that time, its dissociation, degree of dissociation will be higher. So degree of dissociation depends on the solvent. For the polar solvent, have the higher degree of dissociation. For the non-polar solvent, for the non-polar solute, it will have the higher degree of dissociation. Okay. Number 3 point that is very important, the concentration. Concentration, if the concentration of the electrolytes is higher, its degree of dissociation will be lower. So we can write degree of dissociation is inversely proportional to the concentration. Higher the concentration means higher will be, lesser will be the dissociation, degree of dissociation, and that we will understand later on. In the next, we will discuss about this, how it is, so what is exact relation between this concentration and the degree of dissociation. So if the solution is diluted, then it will have the capability of, it will have the higher degree of dissociation. Then fourth point, that is the temperature. Higher the temperature, higher will be the dissociation. This is very thumb rule, higher temperature means higher of degree of dissociation. And fifth number point, the effect of other electrolytes. Effect of other electrolytes. Effect of other electrolytes, how it is going to impact? Now, if these electrolytes have the common ion, then it will suppress the degree of dissociation of the other electrolytes. So, common ion effect, that we will discuss later on in a separate chapter. So, effect of the other electrolytes, temperature, concentration, solvent and solute, all the 5 things that is going to influence the degree of dissociation. Okay? Very important thing, that Ostwald dilution law. This is for the weak acid. For weak acid, suppose it is HA. HA is the weak acid and it is having the degree of dissociation. It is having the degree of dissociation is alpha. So we can write HA aqueous this is the equation of the dissociation of this weak acid, HA weak acid, and it will be converted into some ions and it is unionized ions. So suppose initial concentration of this acid is C mole per liter and it is 0. At equilibrium, when it is reached the equilibrium, so what will going to happen? The concentration, molar concentration of the unionized HA will be C minus CW and it is C alpha and C alpha. So we get the dissociation constant, that is C alpha into C alpha divided by C minus C alpha. So if we further classify this C alpha square, this C into 1 minus alpha, and you can see that this is a weak acid, so we can assume 1 minus alpha is equal to 1. So we can say K is equal to C alpha square by 1. So this can be written as alpha is basically, you can say K by C the root. So degree of dissociation, you can see that is inversely proportional to the concentration, the square root of this concentration. Suppose we have taken 1 mole and the volume is V, then it can be further written like this K into V. That shows this degree of dissociation is directly proportional to the square root of the volume. So you can understand this very important relationship between the degree of dissociation and the concentration and also the dissociation constant K, and here also you can see the volume. This equation is only applicable for the weak acid, because for the strong acid we already discussed alpha is equal to 1, and for that you can say Ka is equal to actually close to the infinity. So this equation will only applicable for this. And for the base also we have the similar equation. Suppose this is a base MOH aqueous, right, and this will have this equation M plus OH minus aqueous, and we will get this type of equation, that is alpha is equal to this Kb is the dissociation constant of a base, weak base divided by its concentration. So these are the very important equations that we can see, and from this equation you have to solve different type of numericals that will now we discuss. This is a very interesting problem. The numerical you have given that if the ionization constant of acetic acid is this 1.8 × 10⁻⁵ at concentration, at what concentration you have to this will be at what concentration will it be ionized to 2%? Will it be ionized 2%? Means you have been given the two things, that is you have given Ka, that is 1.8 × 10⁻⁵, and you have been given the alpha, that is 0.02, and from this you have to calculate this. Now the acetic acid, when it is ionizes, it will be this CH3 minus plus H plus. So suppose initial concentration is C, there is 0, and now it will be C minus C alpha, that is C alpha and C alpha. So you get the Ka is equal to C alpha whole square divided by C minus C alpha, and that is given by this formula, that is C into alpha square. Because you have to, as it is a weak, that we have to weak acid, that we can neglect this, and from this you get that alpha. We have to calculate the C concentration. C you have to calculate, that is Ka by alpha square. Now we will put this value Ka, that is 1.8 into 10⁻⁵, and divided by alpha square, it is 0.02 the whole square. So if we calculate this, we will get this value 0.05 mole. Well, it means 0.05 moles. If we have the concentration of this acetic acid, then it will be dissociated to 2%. Okay, this type of question will come. So that is all for today's lecture. Hope you understand all the things that I have trying to discuss with you. If you have any problem, you can comment in the comment section. Thank you very much. In the next lecture, we will discuss about the concept, acid-base concept of different scientists. All the best and be best. Thank you.